On February 19th, 2022, I got to climb into the Cave of Doom while it was hit by giant lightning bolts from a huge Tesla coil. Here's a little video about it. We believe in science and Faraday. The reason that I said I trust physics and Faraday is because I knew that the Cave of Doom was actually just a Faraday cage that was protecting me from the electrical effects from the Tesla coil. Which brings up a really interesting question. How and why did Michael Faraday build the first large Faraday cage, a giant cube that was big enough for him to live in? And why did he do this in 1837? 50 years before Heinrich Hertz discovered radio waves, and 56 years before Nikola Tesla invented the Tesla coil. This video is going to be split into 4 parts. First, a little background of the people, namely Benjamin Franklin and Charles Coulomb, whose experiments inspired Faraday. Second, a description of what Faraday did in the 1830s to create the cage. Third, I will talk a little bit about the actions of a young Irish scientist named William Thomson, who was later ennobled Lord Kelvin, and how that led over the years to the Faraday cage becoming more popular, and how Faraday's and Thomson's actions led to the cage being used with Heinrich Hertz's radio waves and with Nikola Tesla's coil demonstration. Fourth, I will go through a whirlwind overview of the influence of the cage, specifically how knowledge of the Faraday cage led to the discovery of the electron, how the Faraday cage is used in microwave ovens, and even EMPs and protection devices. Ready for the wild story? Let's go! Electricity, electricity. Part 1, inspiration. In my mind, the story of the Faraday cage does not start with Michael Faraday in 1837, but 82 years earlier with Benjamin Franklin in 1755. This was 3 years after Franklin had done his famous key and kite experiment in an electrical storm, and he was still trying his best to figure out how storm clouds created and stored electrical charges. For that reason, Franklin did a lot of experiments electrifying differently shaped objects and studying how the charges were distributed upon them. This is why he electrified a silver jar and decided to study the charges inside the jar. Now, Franklin knew that if a neutral object was placed near the outside of a charged jar, the neutral object would be attracted to the jar, and if the object touched the outside of the jar, it would gain some of the electricity from the jar and then be repelled by this jar. In this experiment, however, Franklin tried electrifying a silver jar and then lowering a ball into the inside of the jar. To Franklin's shock, the ball was not attracted to the jar. Moreover, if the ball touched the inside and then was retrieved, the ball would remain neutral. In other words, not only did Franklin inadvertently discover that electric charges are all on the outside of a conductive material, he also found that the inside was shielded from any and all electric effects. He was completely flummoxed by this result, writing a friend, "The fact is singular. You require the reason. I do not know it. Perhaps you may discover it, and then you would be so good as to communicate it to me." The reason I know about this experiment is that 14 years later in 1769, Franklin included his description of this experiment in his 5th edition of his book on electricity. Then in 1776, Franklin went to France and tried to use his fame from electricity to help get support for the American Revolution. This was a resounding success. John Adams, a man who personally hated Franklin, wrote that in France, Franklin's reputation was more universal than of Leibniz or Newton or Frederick or Voltaire, and his character more beloved and esteemed than any or all of them. In Paris, one of the many people interested in Franklin's visit was a 40-year-old mechanical engineer named Charles Augustin Coulomb. And it was when Franklin arrived in France that Coulomb learned about a contest to make a very sensitive compass, which inspired Coulomb to not only create a compass, but also study the twisting force and create the torsional scale. Perhaps inspired by Franklin's visit or by the electricity rules he learned in school, Coulomb started using his new torsional balance to study the electric forces. By 1785, Coulomb experimentally determined that the electric force is proportional to 1 over the distance squared, which he declared to be a fundamental law of electricity. The following year, in 1786, Coulomb decided to recreate Franklin's experiment with a silver jar, and even with his super sensitive electricity meter, he determined that when a conducting body is charged with an electric fluid, it is only diffused over the surface and does not penetrate into its interior parts. It was actually Coulomb's experiment that initially inspired Faraday to make his cage, which brings us to part 2. Faraday and his cage. I would like to fast forward to Michael Faraday in 1831. I picked that date in particular because that is when Faraday discovered how to induce electricity with moving magnets or changing magnetic fields. This was huge news. Faraday's biographer and friend said, after the discovery of magnetoelectricity, Faraday's fame was so noised abroad that the commercial world would hardly consider any remuneration too high for the aid of abilities like his. However, Faraday felt like he couldn't have honors or money and still dedicate himself fully to science. Faraday described it as a decision between wealth or science. And with the support of his beloved wife Sarah, they chose science. Faraday thus declined every honor and financial reward that came his way, and as his wish, remained plain Michael Faraday to the last. Beginning in 1831, Faraday started writing paper after paper titled Experimental Researches in Electricity, eventually writing 30 papers with that title, much of which affects our life and language to this very day. For example, in a single paper from 1834, his 7th in 3 years, Faraday created the names anode, cathode, electrolytes, electrodes, anions, cations, and ions. When a friend wrote him a complimentary letter about his work in 1835, he responded, "Your letter was quite refreshing, for I'd begun to imagine that I'd thought more about electricity and magnetism than it was worth. And so a notion was creeping over me that after all I was perhaps only a bore to my friend." By the pivotal year of 1837, for 11th paper on experimental researches in electricity, Faraday decided to re-examine old experiments with their new knowledge. Or as he put it, the science of electricity is in that state in which every part of it requires experimental investigation, not merely for the discovery of new effects, but what is just now of far more importance, the development of the means by which the old effects are produced. See, Faraday had read Coulomb's 1768 paper, and to Faraday, the fact that the electricity is shielded on the inside of a conductor was proof that electricity wasn't created or destroyed, merely moved by the electrical forces. As he put it, the beautiful experiments of Coulomb's are sufficient if properly viewed to prove that conductors cannot be bodily charged. Faraday then wondered about insulators or non-conductors, as he felt that with regard to non-conductors, the conclusion does not at first seem so clear. However, after various experiments, Faraday decided that it was true for insulators as well, noting that, for example, if you electrify a piece of glass with one charge by contact or proximity to charged conductor, it was always found that a portion of the inner surface of the conductor or another part of the glass itself was in an equally opposite state. To examine this further, Faraday decided to study air, as air is an insulator. And that is why he decided to up the size of Franklin's and Coulomb's experiment to make it into a giant cage. Here is how Faraday described it. I had a chamber built, being a cube of 12 feet. A slight cubical wooden frame was constructed, and copper wire passed along and across it in various directions, so as to make the sides a large network, and supplied in every direction with bands of tinfoil, so that the whole might be brought into good metallic communication. After various experiments inside the cage, Faraday turned it around and had an assistant conduct experiments outside the cage, while he, as he dramatically put it, went into the cube and lived in it. Faraday therefore discovered that when he was inside the cube, he was protected from all the electric experiments happening outside of it. Faraday recalled, I put a delicate gold leaf electrometer within the cube and then charged the whole by outside communication very strongly and for some time together. But neither during the charge nor after the discharge did the electrometer or air within show the least signs of electricity. He added that he couldn't see any electric effects, though all the time the outside of the cube was powerfully charged, and large sparks and brushes were darting off from every part of its outer surface. Faraday was happily convinced by this, and concluded that non-conductors as well as conductors have never yet had an absolute and independent charge of one electricity communicated to them, and that to all appearances such a state of matter is impossible. A conclusion that scientists agree with to this very day. After this experiment, in the same paper, Faraday wrote about how he tried to recreate the torsion balance electrometer of Coulomb, but with certain variations and additions. The biggest of which is that he coated his electrical measurement device in stripes tinfoil so that they would be protected from stray electric fields. In other words, immediately after inventing the Faraday cage, Michael Faraday turned around and used it to protect his electric device. Tragically, Faraday's work started to slow in the late 1830s as he started to suffer from stress, anxiety, and memory problems, probably caused from his work in the 1820s making glass and dealing with heavy metals without protective equipment. In December 1839, Faraday's doctor recommended rest to keep him from a breakdown. This didn't help, and by the summer of 1840, 48-year-old Faraday wrote a friend, "This is to declare that I'm not able to bear much talking, being at present rather weak in the head and able to work no more." This is not to say that Faraday completely stopped working, just that after 1840 his work came in fits and spurts. Part 3, Development of the Cage. The biggest early promoter of the Faraday cage was not actually Faraday, but a young fan of his named William Thomson. Thomson had learned about Faraday as a teen from his tutor and became, as he put it, inoculated with Faraday fire. He then got to meet his hero at a conference when Thomson was just 21 years old. They became quick friends, and Thomson then inspired Faraday to conduct an experiment that led Faraday to come up with the idea that maybe light was a wave of electric and or magnetic fields. Thomson didn't initially really like the idea of light being an electromagnetic wave, but it wasn't enough to keep him from recommending Faraday to his younger friend James Clerk Maxwell, who ended up writing Maxwell's equations based on Faraday's ideas. Meanwhile, Thomson continued to promote Faraday and most of his ideas, including the Faraday cage. For example, in January 1860, Thomson complained that even the best of ordinary electrometers hitherto constructed often give incorrect results, as the inner surface of the glass is liable to be electrified. Thomson then lamented that Faraday long ago showed us how to obviate this radical defect by coating the interior of the glass with a fine network of tinfoil. And it seems strange that even at the present day, electrometers should be constructed with so bad and obvious a defect, uncured by so simple and perfect a remedy. Thomson then added the word cage when he noted that a cage made like a bird's cage may be substituted with advantage for the tinfoil network. During this time, Faraday's health continued to deteriorate, and by March 12, 1862, Faraday conducted his last experiment at the age of 70. He wrote a friend, "Again and again I tear up my letters, for I write nonsense. I cannot spell or write a line continuously. Whether I shall recover this confusion, do not know. Faraday did not recover and died on August 25th, 1867, at the age of 75. As his wish, he had a plain, simple funeral, attended by none but my own relatives, followed by a gravestone of the most ordinary kind in the simplest, earthy place. A few weeks after Faraday's death, a now knighted Sir William Thomson was on a committee to make standards for electrical resistances. In this report, Thomson stated again that it was a shame that people don't use Faraday's system to protect their electronic equipment, and then added that the electroscope he was using was protected by using a, quote, Faraday metal cage. And thus the term Faraday cage was born. 12 years later, in July of 1879, a 22-year-old graduate student named Heinrich Hertz heard about a contest to experimentally prove the theory of electrodynamics, which was brought forth by Faraday and was mathematically executed by Mr. Maxwell. It took Hertz 8 years, but in 1887, he discovered that if he added an antenna to an induction coil, it would make an invisible electromagnetic wave that he could catch across the room as a spark in a circular wire with a tiny gap in it. These waves were initially called Hertzian waves, but by the 1920s, they were called radio waves, a name that they've retained to this day. As radio or Hertzian waves were created by vibrating electricity and they move at the speed of light, this seemed like a validation of the Maxwell-Faraday theories of the nature of light. When William Thomson heard about it, he thought that these new Hertzian waves would make it through a Faraday cage, saying, "We all know how Faraday made himself a cage, and he saw no effects on his most delicate gold leaf electroscopes in the interior." But Faraday's attention was not directed to look for Hertz sparks, or probably he might have found them in the interior. What Thomson didn't know was that in July of 1889, Hertz tested out Faraday's cage on his new radio waves and found that they blocked alternating fields too. For when Hertz placed his spark gap in a wheel of wires, he found that not the slightest electrical disturbance would be detected in the wire, in whatever direction waves were sent through the apparatus. It was around the same time that Hertz was experimenting with Faraday cages that Nikola Tesla learned about Hertz's experiments with radio waves. Tesla later recalled that the publication of Dr. Heinrich Hertz's result caused a thrill as has scarcely ever been experienced before. Tesla then concentrated his attention on the production of a powerful induction coil, which eventually led to the development of very high voltage Tesla coils. To Tesla's delight, his new coil could make giant sparks and could even electrify fluorescent lamps if they were held near the coil. Tesla burst on the scene with these amazing displays in 1891 that even 12 years later were described as the most remarkable lectures ever delivered before a scientific audience. Tesla's coils were actually at a lower frequency than Hertz's, and it was quickly found that a Faraday cage could block the waves from a Tesla coil as well as from radio frequencies. And soon Faraday cages were incorporated into the Tesla coil demonstrations, as they continue to this very day.
Bigger coil. I got a couple of containers to put these some tubes in. One's glass, an insulator. I got a birdcage.
Part 4, Influence of the Cage. 6 years after Tesla demonstrated his coil, in 1897, a shy Englishman named JJ Thomson, no relation to William Thomson, used his knowledge of the Faraday cage to discover electrons. See, in the 1890s, Thomson was confused because Heinrich Hertz, the same guy who had discovered radio waves, had been unable to move a beam in a cathode ray tube with electrified plates, even though another scientist had determined that the cathode ray had a negative charge, and it was well known that a beam could be moved with a magnet, just like negative electrical charges moving in a wire. JJ Thomson then realized that the trace amount of gas in the tube was becoming electrified and screening the cathode ray from the effects of electric force, just as the metal covering of an electroscope screens off all external electric effects. In other words, JJ Thomson realized that the trace amount of air in the tube was becoming ionized and acting like a Faraday cage. Thomson then devised a more powerful tube so he could remove more air, so that there was not enough air to be a Faraday cage and the beam could be moved with electric forces. Then the interaction between the electric force and the magnetic force is how Thomson determined that the cathode ray was composed of tiny negatively charged particles that are in everything. We now say the cathode ray is a beam of electrons. As technology improved, there became increased interest in Faraday cages to protect delicate electronic devices and to protect ourselves. For example, one day in 1945, a man named Percy Spencer was experimenting with microwave radar. I mention this because one day at a particular frequency, Percy found that the Mr. Peanut Bar in his pocket melted. After testing it out with popcorn kernels, yes, the first microwave popcorn, and an egg, which exploded, Spencer realized that these waves, which are just high frequency and therefore smaller waves or microwave radio waves, happen to have just the right frequency to make water and objects spin and thus heat food up. Spencer immediately filed for a patent for a microwave conveyor belt. 2 years later, Spencer redesigned it into what he called a microwave oven, where the oven was made of conductive material so that it would act like a Faraday cage and protect the operator. In another example, in July of 1962, the US military tested out a 1.4 megaton hydrogen bomb, about 100 times more powerful than the bomb used in Hiroshima, at about 250 miles above an island in the Pacific. To the surprise of physicists, this bomb created artificial aurora borealis, hard to say, all over the place and caused circuit breakers to pop and burglar alarms to ring 800 miles away in Hawaii. It took several years to figure out what was going on, but by 1967, scientists determined that gamma rays from the bomb had interacted with the lower Van Allen belt, creating a huge electromagnetic pulse, which they called by its initials EMP. At first, people weren't really worried about EMPs, as most of their technological equipment was built with vacuum tubes, which tend to be pretty impervious to damage from the very short spike of an EMP. However, with the rise of semiconductor technology and with wireless communication, there became more and more worry about the effect of EMPs. By 1980, the U.S. Secretary of Defense publicly worried about the widespread loss of connectivity, which would be caused by a high-altitude nuclear explosion and its resulting electromagnetic pulse. By July of the following year, a scientific reporter named William Broad wrote a series of articles for Science magazine with the alarming subtitle, "A single nuclear blast high above the United States could shut down the power grid and knock out communications from coast to coast." Many governments took these warnings seriously and did measures to protect their equipment, but the general public became convinced that a single nuclear bomb would disarm all electronics, and soon movies were showing EMPs causing planes to just drop out of the sky. My favorite example of this is a really campy movie from 1996 called Broken Arrow. In this movie, an evil John Travolta detonates an underground nuclear device that instantly destroys all of the operational electric devices and causes a helicopter to crash. When Travolta was told that the shockwave took down the damn chopper, he responds, "That was an EMP, electromagnetic pulse, nuclear blast sends it out for miles, everything electronic just shuts down, including the choppers and radio. Note that this movie is just wrong. Small underground nukes do not create a huge EMP, and even if they did, airplanes and helicopters tend to be pretty safe as they're made of metal and by themselves are Faraday cages, which is why they are safe when struck by lightning. In addition, it is possible to protect most equipment from an EMP with Faraday cages and surge protectors, which is called hardening the equipment. That is why most data centers and power centers are put behind metal gratings or metal walls. That is not to say that an EMP from a large nuclear device exploded high up in the atmosphere would be harmless, as it would take a lot of money to protect everything, and so it is often skipped. For example, in 2019, the Electric Power Research Institute declared that the worst-case EMPs could cause widespread electrical damage on the order of several states or larger. However, luckily, none of the scenarios that were evaluated resulted in a nationwide grid collapse. Of course, a large EMP blast could easily fry some of your personal electronic devices, and even a statewide electric grid failure could be pretty catastrophic, which is why people sometimes buy or make Faraday cages to protect their equipment for such a scenario. In addition, with the rise of wireless communication, there was an increased interest in using Faraday cages to protect your devices from electronic snooping. This is another reason for the portable Faraday cages to protect your cell phone. This, for example, is why the US government creates secure places to share secret information called a SCIF, which are at minimum a big Faraday cage to protect the people inside from outside interception of data. For all these reasons and many more, Faraday cages are abundant in electrical engineering. This brings up another question. What is happening with the electrons in the cage that protects you inside from lightning and from some electromagnetic waves, but not from others, not from the ones of visible light? I will use a 1843 experiment by our friend Michael Faraday with an ice bucket to explain the physics in detail of the Faraday cage next time on the Lightning Tamers. So that was the long history of the Faraday cage. I am really excited to announce that we have a launch date for my book. Ready? Boom. The Lightning Tamers, true stories of the dreamers and schemers who harnessed electricity and transformed our world, is coming out October 12th, 2022. Check out my website, www.kathylovesphysics.com. You can find links to my email list so you can join my email list. You can find links to my Patreon page so you can become a Patreon if you want. Thank you, patrons. You will learn everything about when you can pre-order my book, which should be in next month in June 2022. Sorry about the long wait. There's a 4-month gap between when the book is formatted and when it will be available, and that's because I need a little time to promote it. Speaking of which, if any of you know anyone in radio, doing podcasts, doing YouTube interviews, who does technical reviews for a newspaper or a magazine, or is famous in any way, shape, or form, and might be interested, shoot me an email. I'm at Kathy@kathylovesphysics.com. Not hard to remember. And hook a gal up. And if you don't have anything like that, try posting something on social media. Maybe your friends and neighbors do. And if you hate social media and you have no friends and no neighbors, you can always give me a thumbs up. That always helps. Okay, stay curious and safe. Bye. Let me try it again. On February, it's kind of wheezing. On February 19th, 2022, corpuscles. That's just so wrong. Which he called corpuscles. Corpuscles. I can't even say it. We now say that the cathode ray beam is a beam of electrons.